Discussing Prith Banerjee from ANSYS, he gave a presentation about AI and physics. He is the CTO of ANSYS, and I think it's really important to understand what they're doing in the grand scheme of things of real-world AI. So it's related to the Tesla conversation, which will be discussed in a separate episode, the Tesla earnings call, and the particular conversation about real-world AI. But I think real-world AI is becoming a thing. NVIDIA is investing. Synopsys bought ANSYS for that reason for about $30 billion. Tesla is investing massive amounts of money. What is real-world AI, and what is Prith teaching us about real-world AI? So let me give a brief overview first. What is ANSYS? ANSYS is a traditional simulation company. Now, traditional simulation is, think of second-order differential equations, partial differential equations. So you have these massive linear systems, dynamic linear systems, where one variable changes, other variables change, and the reason it's differential equations is because the changes in variables affect everything else. As he said in the presentation, one of the biggest successes of this type of approach has been in fluid dynamics, chemical engineering. I remember back in my days when I was doing derivative research, we used a lot of mathematics from chemical engineering or fluid dynamics to model complex evolutions of systems with lots of variables in derivatives. The variables are things like interest rates, equity prices, and so on and so forth. And in physics, of course, it's other stuff. But in the end, the problem is the same problem everywhere. The problem is that you have a dynamic system which depends on lots of variables, and you want to simulate how those systems evolve. And I think the big culture shift, there's a big culture shift happening in the engineering community, is that these variables used to be learned in a sense that you would guess them, learn them, read them in physics books, and most importantly, you would only use variables that you know about. Versus the new approach, the learning-based approach, is you have many, many more parameters. Let's not even call them variables anymore, and you learn them. Now, in order to learn them, you have to observe the system. And I think this is the key of this presentation. I actually asked Prith about this. Like, in order to become an AI simulation company, ANSYS really has to become a data pipeline company. Now, not to diminish the algorithmic work and the whole software and hardware infrastructure work that is necessary to train massive models. But first and foremost, you have to have the data. If we take Tesla as an example, Tesla is investing a lot in GPU clusters, investing a lot in algorithmic solutions, but most importantly, they're investing in data collection, data filtering, understanding which data is even good for learning, which data is useless for learning. Those are the kinds of problems that Tesla has been trying to solve for years now, and that's why they're ahead in real-world AI. And I think fundamentally, ANSYS or whoever else wants to tackle real-world AI is going to have to solve that kind of infrastructure-wide problem. And I think in my discussion with Prith, I could see there's a fundamental problem that we often underestimate, which is, he said that when I asked him, look, is ANSYS ready to turn itself into a massive data pipeline company? And he said, yeah, but not enough. He said, I want to talk to my CEO and say, listen, OpenAI is investing tens of billions of dollars into compute. My CEO doesn't want to do this. And the same is happening over at Tesla, right? There's billions and billions being invested in AI infrastructure and data collection and data pipelining. And that's what it takes to build systems that are truly, truly transformational. And it doesn't look like ANSYS has the kind of guts to do that. And I think this is a lesson you can learn about ANSYS, but more importantly, you can learn a lesson also. And the purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. And I think it's really crucial for us here at Orange Capital Partners and generally in the hedge fund community to understand, look, what does it take to create wealth, right? It's knowledge, it's science, but it's most importantly entrepreneurial guts, entrepreneurial risk-taking abilities. And that, I don't mean like crazy, throwing darts at the wall kind of thing. I'm also not talking about the venture capital approach, which is, to paraphrase Mark Andreessen, like we don't need a strategy. All we do is just invest in pretty much everything, and then hopefully something sticks. No. This is very different. Like you have to have a clear vision, a clear North Star, and you have to commit. You have to go all in, not just as a CEO, but you have to bring your people on board. You have to fully vertically integrate and then build the system. And I think that's what's lacking at ANSYS. That's why I don't think ANSYS will solve the real world problem. I don't think that ANSYS will solve physics. But let's abstract from that and just talk in general about what is the actual problem. So physics simulation requires, of course, understanding physics. And like I said in the beginning, traditionally, or like if we want to understand physics, we need to have some sort of model. And the model consists of variables, and those variables influence a system based on physics. And that's what we mean with understanding physics is if we have, let's say, the Newton equations are a model of the real world, which is pretty good, pretty approximative. We have general relativity, which is even better. And we have quantum electrodynamics, which is very good at sort of the small scale when we talk about waves and light. But in general, the problem set is the same, right? We have a certain model, and the model consists of variables, and then those variables change, the system changes. And the difference between old school engineering and sort of the new data-driven learning is old school engineering would take the variables as either fixed or maybe learn the variables through observation in experiments, but it would build deterministic differential equations where the variables are fixed and then the equations evolve based on those fixed variables. Versus the new type of learning, it's the actual variables that you're learning. And we don't call them variables anymore, we call them parameters. And we don't even give them names because we don't really care whether something is called density or gravity or whatnot. All we care about is that the system acts well in the real world, whether it's a self-driving car or whether it's designing a chip with certain thermal properties, or whether it's designing a battery with certain thermal and electrodynamic properties. We only care about the actual influence that the environment has on the system and the system has on the environment. And that can be learned through parameters. So this is the big shift. And I think that's what this presentation was really about. Now, he talked about high performance computing and digital twins, but I don't even want to go there because the real solution of real world AI is in developing data pipelines that can then help you approximate a function approximators. And the way you approximate functions is by having parameters learn from interaction with the real world. This is really what it's about. Now, like I said, I spoke with the gentleman about, let's say, how ANSYS tackles this problem, and what I sensed is a bit of a there is a culture gap between traditional engineering and learning-based approaches towards solving problems. The engineer of the future is going to build the machine that is going to solve the problem. And to build the machine, you have to teach the machine. You have to teach the machine. And the way you teach the machine is by, at least fundamentally, by observation and theory. Now, observation and theory are two sides of the same coin, right? We can't just say all we need is observation because observations are theory a lot. And what we see is based on our theories, and our theories are based on what we see. So in other words, we need both. For example, yesterday when I spoke with Johanna Nelson Wheeler about building X-ray machines for battery degradation research, you need to build the machines to be able to see at the granularity that is necessary to understand the batteries. So we have to build a theory of what we actually want to see, and then we have to see it, and then start building models based on that. So this is a good example of a potential application of a physics-based AI, in this case for battery degradation. Actually, Synopsys bought ANSYS for exactly, not exactly, but a similar reason. But what Synopsys wants to become, according to Prith, is they want to go from chip design and solve chip design problems to system design. We build whole systems like airplanes, batteries, electric cars. And for that, they need to have more physics simulation. That's why they're buying ANSYS. I think it's an interesting situation. I just don't think that the culture of the company is there for a real big orders of magnitude type wealth creation. I think this is going to be more of a, decent growth, double-digit kind of growth situation, which is great and really worth investing. But we're interested in the big stuff, in the high risk, high reward type stuff. And high risk, high reward really means that you put your eggs on certain baskets that have very, very high promising returns based on the fact that you're building scale in order to solve really big problems. And what I mean with scale is, you're building a data pipeline and you're building compute and memory pipelines that can handle a massive amount of data to solve, let's say, certain physics problems. So to summarize again this presentation, I think it was illuminating for us because we learned from this presentation that the physics simulation problem is real. It's out there. Everybody's talking about it. Tesla's a leader because they have the data and the compute pipeline and the desire to invest massive amounts of money into solving real-world AI problems. ANSYS is certainly also on track because of their legacy, but there's a massive shift away from traditional electrical engineering type solutions, which is based on differential equations and having fixed variables and then looking how the system evolves, into learning parameters and not variables, and then having the learned parameters function approximate the behavior of a physical system. Thank you.